Hello, I would like to thank the organizers for the invitation. With focus at the late time boundary of the sitter, and we want to gather some clues for holography on the sitter. This will mainly be based in a way that it can be used immediately for early universe cosmology, but I will end the talk to open up a question on how we may use this information to understand dark energy as well. So Friedman Robertson Walker cosmology deals with the time dependence of the universe. Universe changes its geometry through time, and how to deal with the time dependence of the background will be one of the underlying themes. Within all our knowledge so far, based on theory and observations, we know that our universe underwent an epoch of accelerated expansion at least twice in its history. One of these epochs is the early inflationary phase. The other one is dark energy, which is the focus of this workshop. The geometry relevant in both of these epochs can be idealized by the de Sitter geometry. Not just for cosmology, but de Sitter geometry is an interesting place to ask how to set up quantum field theory and holography, and as well as how to do cosmology. So cosmology teaches us about the history of our universe, quantum field theory teaches us about fundamental particles, and holography gives a conformal point of view to gravity. So we will collect all these things, universe, fundamental particles, gravity, together by focusing on what the de Sitter geometry has to say. The overall theme is to focus on symmetries of the de Sitter space-time and organize our discussion with respect to the unitary irreducible representations. So first, I will tell you the symmetries, and then I will tell you the representations. So let's start with the geometry. De Sitter is one of the solutions to the Einstein equations. It's one of the maximally symmetric solutions in vacuum with the presence of a cosmological constant, where the cosmological constant is positive. So with these 3 bullet points, it actually lives in a bigger family of spacetimes. In global coordinates, spatial sections look like spheres that are growing in time, hence the accelerated expansion. We can consider a Penrose diagram of this space-time. It looks like a square. And studying the Penrose diagram, we see that it has 2 boundaries, and you reach these as you travel along time. One of them is the early time boundary, the other is the late time boundary. Another set of coordinates that is of use in cosmology are planar patch coordinates. Here the metric looks as follows. In these coordinates you have full access to the late time boundary, but you just pick up a point from the early time boundary. Notice that there are no global time-like killing vectors. If you consider time translations, your metric will not remain invariant. Instead, you have dilatations, which look like what the time translations are being replaced with. So we will focus on this part of the sitter, and this is the one used in early universe cosmology. Why focus on the late time boundary? What I mean that this has a holographic content to it. Imagine walking at the sea. The steps you take create ripples on the sea surface. So think of the surface of the sea as the boundary. Holography tells you a duality about what happens in the bulk of space-time. This is like the inner volume of the sea. So whatever happens there gravitationally, there's another way to describe it by another theory that captures what happens at the boundary. So what holography hopes to give you is a list of operators and correlators which capture physics at the boundary. So this is what we want to look for. We want to look for a list of operators and correlators at the late time boundary of de Sitter. So how do we do this in the coordinate system we picked, which is mostly used in early universe cosmology? So what do we do in early universe cosmology? We compute and observe 2-point functions. And we have a way to shape their momentum dependence. And various instruments measure this. They measure the exponent that keeps track of the momentum dependence to be almost 1, means you have scale invariance. This is exactly the type of 2-point function you get if you study a free massless scalar on de Sitter. What is meant by mass here is what you write as the coefficient of the quadratic term in the action. Whether this captures physical mass is a completely different discussion. Scale invariance, this is a feature of conformal field theories. One idea about gravitational anti-de Sitter being due to a conformal field theory, maybe you can have something like this for de Sitter. So later on, people say if we figure out how to work with DSCFT, it may tell us why we observe things the way we do. So along the way, people also start focusing on the representation theory aspects of it. One of these works is trying to set up a CFD dual to higher spin theory on de Sitter. And in this leftmost paper, they actually go and do wave function computations for 2 different types of representations. They point out that if you focus on another category of representations, which are actually easier to study on de Sitter, these are principal series, you will see big differences to what you expect just from ADS-CFD. Maybe we should sit and do things from scratch for de Sitter, and we can focus on the representations as a clue. So if we think of de Sitter as a member of a bigger family, so these are all vacuum solutions, these are all maximally symmetric spacetimes, but the difference is that they all capture different signs of the cosmological constant. And Minkowski is where we have our best understanding of quantum field theory, and you can say anti-de Sitter is where we have our best understanding of holography. But if we try to address these frameworks for de Sitter, we will not only be learning about de Sitter, we will also be learning about how far our framework, our tools go. So with all this introduction, let's look for a list of operators and correlators as clues towards setting up a holography for de Sitter, with the hope that this may give us new insight on observations. By a list of operators, we will look for things we can associate to unitary irreducible representations of the de Sitter group. And this brings us to the free quantum field theory on de Sitter and what physical content it carries. Now, the representations of the de Sitter group are well known. So as we think of de Sitter in a family, let's kind of compare it with Minkowski. These are the set of coordinate transformations that leave the metric of the spacetime of interest invariant. So, and they form a group. For Minkowski, you have invariance both under time translations and spatial translations, whereas time translations are not isometries of de Sitter spacetime. Instead of having boosts and time translations, on de Sitter you have dilatations and special conformal transformations. So these are very general scaling transformations, and these are the kind of transformations you encounter in conformal field theories. So the first clue to look for a conformal field theory dual comes from just matching the symmetry. So we have to learn how to deal with absence of translations, and instead we have to embrace these scaling transformations, and especially we have to embrace dilatations. So these difference in the set of symmetries also give a difference to how you label representations. This chi stands for the labels of the representations. On both space-times, spin is important, it is a label, but due to presence of time translations or Minkowski, you have mass as a label to label physical states, whereas having switched time translations with dilatations, you have another label which keeps track of how things transform under dilatations. So this is if I rescale the coordinates, an object of interest gets rescaled by an overall exponent. Exponent is called the scaling dimension. Labels the object of interest. But for the Sutter group, the scaling dimension has a specific format. There's a part of it that keeps track of number of dimensions, and another part that keeps track of mass and number of dimensions. So since once you say I'm working on DS4, let's say, you fix the number of spatial dimensions, really what can vary from a field of interest from one field to another is this piece. So this free part that will carry information about the field of interest is the one that labels the representation. Now if you compare, so these are the labels, but also the way you break down representations into categories are different. And we said the representations are going to be labeled by the scaling dimension. For principal series, this is fine, this is unitary. In the cases of real scaling dimension, the category of the representations break further into categories. And here, so all of these are unitary representations. There are some limits on the range of the labels, and this list is for bosons, in fact for spin 0. But what happens is unitarity comes with a well-defined inner product. What that inner product is different in all these cases. So going back to our main message, we wanted to focus on symmetries and find operators at the late time boundary of de Sitter, which we can recognize as the unitary irreducible representations of the de Sitter group. So we started doing this for scalars, and we found two operators with different scaling dimensions for a given mass. Both of them mattered, and they had non-trivial commutation relations with each other. And along the way, we learned that while we can normalize the bulk field modes with the good old Klein-Gordon inner product, what happens for the operators at the boundary and the states they can give rise to is more subtle. There you have to go and look at these group theoretical inner products. In different studies, we considered scalar fields with various mass on various dimensional de Sitter and a massless vector field on 4-dimensional de Sitter. Imposed that they obey Bunch-Davies initial conditions, composed them into Fourier modes in terms of polarization tensors as well in the case of the vector field, and taking a late time limit, studied what operators they give rise to at the boundary. In taking the late time limit, we always found two operators for a given mass, and we checked how these operators can be normalized with respect to group theoretical inner products. Doing so, we managed to find an example to each of the categories of representations. We got principal series and complementary series in various dimensions. principal for heavy, complementary for light scalars. And we found exceptional series 1 representation from the massless scalar on 4D, and exceptional series 2 representations from the massless vector on 4D. One motivation for going off to non-trivial spin is that vector fields, we know these are gauge fields, so we expect to see more and more examples of discrete series here. So now we're actually tracking, we want to track down discrete series, and we set our questions with that motivation. But one thing known about discrete series is they arise as what one of the types of exceptional series break down into. The principal, complementary, and discrete series representations are irreducible. Exceptional series are not irreducible, they're reducible, and in certain number of dimensions, a specific category of subcategory of exceptional series reduced down to a discrete series. Moreover, the discrete series come in two categories themselves, called discrete plus and discrete minus. So we wanted to see this happening by studying the late time behavior of a massless spin-1 field on planar patch de Sitter. And what we learned is that these discrete series labels come from helicity labels. One of these two representations we could show breaks down to the promised discrete series plus and discrete series minus representations, where we made use of duality and anti-self-duality of the field strength tensor built from the gauge field solution we had to identify the plus and minus labels of the two discrete series. So doing all the work, this is what the late time operators boiled down to. Again, so you have two with different scaling dimensions, but they get broken up further into late time operators with helicity labels. So the late time operators without the helicity labels, you can normalize with respect to the exceptional series inner product, relevant exceptional series inner products. And when you do that, what you get is this, one of them is zero norm, that's like just a gauge artifact, but at least one of them survives. And maybe that's okay, that itself breaks down into two different helicity operators. You have two polarizations of photons on Minkowski. That's kind of like finding those two polarizations and only one operator for each on the system. Now, all this was in the planar coordinates. If we go back to our Penrose diagrams, I mentioned that the one we are working with is the one relevant for the early universe cosmology. But in dark energy studies, considering that it is epoch in which we are living, we are observers living in the de Sitter universe. It's not that we are getting information from the late time boundary because we are observing it at some other epoch afterwards. So then the coordinate system for an observer on de Sitter are static patch coordinates. And it would be interesting to see how, where one might recognize unitary irreducible representations of the de Sitter group being realized in the coordinate system that would be relevant for an observer living in the de Sitter universe today, like ourselves, trying to understand the dark energy epoch today. So with that, I Thank you all for your attention.